Hello, today we shall learn finally how to solve a differential equation using Laplace transform. We have to transform the entire equation, apply Laplace to the equation, and we have to see how to transform the derivatives. So in this lecture, we shall derive formulas for the derivatives and show how to solve some simple equations. Our unknown function will be x of t, and its image is the big X of s. So here is the Laplace transform x prime. Using the definition, we write integral 0 to infinity x prime t exponential minus st dt. And this integral we can solve by integration by parts. Here we have one derivative and we here have the exponential. We shall use u to be this exponential, and v prime is x prime. Using the formula for integration by parts, we write here xt exponential minus st, evaluated from 0 to infinity minus integral 0 to infinity x exponential minus st, derivative brings down negative s dt. To evaluate the product x exponential between 0 and infinity, we had to use limits. I'm writing here limit xt over exponential st, t grows to infinity, minus value at 0 will be x of 0, and here bringing s outside and two negatives will give plus, will be plus s integral 0 infinity xt exponential minus st dt. Okay, what we have here in this integral is exactly the big X, the Laplace transform of the function x of t. And the limit at infinity we assume to be 0. So we assume that we're using functions such that exponential st grows faster when s is big enough. And in this case, the result will be Laplace x prime will be minus x0 plus s big X of s. So this is our formula for transforming the first derivative. X of 0 we shall take from the initial conditions. Now the second derivative, Laplace x second, I shall consider the second derivative to be the derivative of the first derivative. So I'm writing Laplace x prime, all this prime, and using the above formula for x prime instead of x. So this will be minus x prime 0 plus s Laplace x prime, replacing x by x prime. Laplace of x prime we can take from the above formula, so this will be negative x prime 0 plus s, and here I'm copying minus x0 plus s big X of s. After simplifying, we have the formula for the second derivative. Here I'm writing Laplace x second will be minus x prime 0 minus sx0 when you distribute s here, and plus s squared big X of s. This is how we transform the second derivative. Now we can continue this way and transform finally transform the third derivative and further, but I'm going to stop because for our equations we just did the first two derivatives. And here our first example. Example 1. Solving examples from section 10.2. I shall do even numbers and homework will be for odd numbers. Here is number 2. Solve the equation x second plus 9x equals 0 with the initial conditions x0 equals 3, x prime 0 equals 4. Very simple equation. Now we can solve this equation. It's a homogeneous second order equation using the characteristic equation. And it's good to do this just to compare. But first I want to show you the Laplace transform. So we apply Laplace to both sides. Apply Laplace, I shall write it this way, to both sides. Both sides of the equation. Laplace x second plus 9x equals Laplace 0. Well, Laplace 0 is 0. And here we distribute to the second derivative and 9x will be Laplace x second plus 9 Laplace x equals 0. For the second derivative, we use the formula from above. And Lx is the big X. So we have minus x prime 0 minus sx 0 plus s squared big X of s plus 9 times big X of s equals 0. At this point we substitute the initial values. X prime 0 is 4, x0 is 3, so we have minus 4 minus 3s plus, let's factor the big X, s squared plus 9 in parentheses, and all this equals 0. And now we solve for the big X. So this is the idea. The differential equation was transformed into one algebraic equation. This is one algebraic equation. The unknown is the big X of s. We shall solve for it and then invert to find the small x. The big X of s multiplied by s squared plus 9 equals 4 plus 3s, bringing these two terms on the other side. So the big X of s will be 4 plus 3s over s squared plus 9. And now we have to find x of t from here. Find the original from image. So we have done this. We have seen similar expressions. What we have to do is break in two different partial fractions. So this will be 4 over s squared plus 9 plus, and I shall write 3 deliberately in front, s squared plus 9. So the second expression is already formula. In our table we search to find formulas with similar denominators, and we find 2 for sine and cosine. Here I shall write them down. When k is 3, comparing denominators, k squared is 9, so k is 3. So we shall use these formulas. Laplace cosine 3t equals s squared plus 9. And Laplace sine 3t equals 3 on top s squared plus 9. So the first one is right here. We can replace immediately. For the second one, we need to adjust. We need to put 3 on top, not 4. And write this way. The big X of S. I shall write 4/3 and here 3 on the top, s squared plus 9 plus 3s over s squared plus 9. And now replacing these two, it's 4/3 Laplace sine 3t plus 3 times Laplace cosine 3t. Collecting everything inside L, this will be Laplace 4/3 sine 3t plus 3 times cosine 3t. And inside the braces we see our original. So the big X is Laplace transform of this function here. So this has to be the small x. Let's write explicitly our solution. 4/3 sine 3t plus 3 times cosine 3t. This is our solution. So that's how it works. We transform the equation into one algebraic equation, solve for the big X, and then invert using different tricks and different techniques, using the table first of all. The initial conditions here are used at the very beginning. When we transform the derivatives, we substitute the initial conditions. When we use the other method, solving homogeneous equation, we write general solution, only after that we compute the coefficients. So let's compare. Solve by using the characteristic equation. The characteristic equation for this will be r squared plus 9 equals 0, just this. And r squared equals -9, r equals plus minus root of -9, which makes plus minus 3i. We have complex roots, and with this we define two independent solutions, cosine 3t and sine 3t for the characteristic equation. General solution will be coefficient with cosine 3t, arbitrary coefficient with sine 3t, and b arbitrary constants, which we could call also parameters. And here we use the initial conditions. When t equals 0, x of 0 is 3, so 3 equals a. Immediately cosine is 1, sine is 0. Then we have to differentiate. X prime will be -3a sine 3t plus 3b cosine 3t. Again, setting t equals 0. X prime 0 is 4, so 4 equals 0 plus 3b. And from here, b is 4/3. So again, we find the same answer. B goes with the sine, a goes with cosine. So when we substitute them here, we get the same answer. Actually, using the characteristic equation is faster, gives you the solution faster, but I'm deliberately doing Laplace transform because we want to learn how to use the Laplace transform. We shall come to equations very soon where the methods of chapter 5 will not work. Let's do another example, solving number 4. Here the equation is x second plus 8x prime plus 15x equals 0 again, homogeneous equation. x0 is 2, x prime 0 is -3. Apply Laplace transform to both sides and distribute. Laplace x second plus 8 times Laplace x prime. So we distribute and take the coefficients out. 15 times Laplace x. And this equals Laplace 0, which is 0. Immediately using the formulas for the derivatives. Minus x prime 0 minus sx 0 plus s squared big X of s plus 8 times, and here we have minus x0 plus s big X plus 15 big X of s, and this equals 0. Okay, replacing the initial values, x prime is -3, so first position we get plus 3 minus 2s plus s squared big X plus 8, here -2 plus s big X plus 15 big X equals 0. Now we regroup. We factor the big X, and all the other terms we bring on the right side. So factoring big X of s, we have s squared from this term, and also we have plus 8s from this place and plus 15. All the other terms go to the right. So this will be 3, and we have also -16 from here. On the left side this will be -13. On the right side becomes plus 13. And -2s becomes plus 2s. Solving for the big X. Big X equals, let's write this way, 2s plus 13, s squared plus 8s, just a second, 8s plus 15. Pay attention that in the parentheses here, when you factor the big X in this denominator, you see this is exactly the characteristic polynomial. So it's good to look here and make sure that you have the right expression. What to do next? We don't have such thing in the table, and we shall try to factor the denominator. So we need to find the roots, if we have real roots, and factor in simple factors. If not, there will be a different technique. So let's see what are the roots. If we set s squared plus 8s plus 15 equals 0, for s we have -8 plus minus root 64 minus 4 times 15 minus 60 over 2. So this will be -8 plus minus 2 over 2. Two different real roots. S1 will be with -5 with plus. The other one will be -3. So this denominator factors then 2s plus 13 over s plus 5, s plus 3. And what next? Next we break this in partial fractions. we shall write this in the form some unknown coefficient a over s plus 5, and then unknown coefficient b, s plus 3. We have to find iota a and b. So we use a technique from calculus when we want to break something, a rational function in partial fractions. Here on the right side we write common denominator, so this will become a s plus 3 plus b s plus 5 over this. The common denominator is the product of these two factors. And then we compare tops. The denominator is the same, so that on the top we have the same expression. 2s plus 13 equals a s plus 3, as plus 3 plus b s plus 5. From this equation we have to determine a and b, and we have two convenient values. When we take s to be negative 3, this term here will be 0. On the left side we have 6 plus 13, negative 6 plus 13 will be 7. And this term is 0, and the other term will be 2. So b will be 7/2. In the same way, we take s to be negative 5. On the left side we have 3. On the right side, when s is negative 5, this is negative 2a. And the second term is 0. So a will be negative 3/2. Excellent. I can write now the big X will be negative 3/2 1 over s plus 5, deliberately coefficient I'm putting in front, and plus 7/2 1 over s plus 3. We can invert very easily. From the table we use the formula for transform of exponential function. Here I shall write it again using this formula. So we can identify for the first fraction a is negative 5, for the second is negative 3. This will be negative 3/2 Laplace exponential negative 5t, and plus 7/2 Laplace exponential negative 3t. Collecting everything inside L, I can write the big X Laplace negative 3/2 exponential negative 5t plus 7/2 exponential negative 3t. Inside the braces we find our solution. X small of t will be negative 3/2 exponential negative 5t plus 7/2 exponential negative 3t. This is it. This is our solution. Now it will be very good to solve this equation again using the characteristic polynomial, the characteristic equation, and it's a very simple method. You find the real roots, they're already here. So with these roots we can say that these two functions, exponential negative 5t and exponential negative 3t, are independent solutions, and the general solution will have the form xt equals some unknown constant a exponential negative 5t plus b exponential negative 3t, different a and b of course, general solution of the homogeneous equation. And then using the initial conditions you can compute a and b, and I hope that my computations are correct, so you get the same coefficients. For these simple cases, when you solve with Laplace transform, it's very good, actually very important, to solve it also like before with the characteristic equation. This is a good review of the material of chapter 5. It will be helpful for the final. Okay, we continue further. Here I shall go now to example 6, problem 6, section 10.2. Solve the equation x second plus 4x equals cosine t. Non-homogeneous already. x0 is 0, x prime 0 is also 0. Our first non-homogeneous equation with Laplace transform. So apply Laplace transform to both sides and distribute. We find Laplace x second plus 4 times Laplace x equals Laplace transform cosine t. Okay, now we're using the formulas that we know. Minus x prime 0 minus s x0 plus s squared big X and plus 4 times the big X. The big X is big X of s. On the right side, transform of cosine will give you s squared plus 1. K is 1. X prime 0, x0 zeros. So factoring the big X on the left, we have s squared plus 4. And on the right side, we have s squared plus 1. Solving for the big X of s will be s over s squared plus 4 times s squared plus 1 in the denominator. Now we have to invert, find the small x. Again, we had to use partial fractions and break these two. How to break? When we have to use partial fractions and the factors in the denominator have squares, theory requires to look for coefficients as plus b on top, s squared plus 4 denominator, and then another similar cs plus d on top, s squared plus 1. So if you have a quadratic factor on the top, you put a linear factor. And we have now 4 coefficients involved in this problem. Again, we can write common denominator, compare coefficients, and find a, b, c, and d. Now I want to show you a shorter method. So we shall just take first 1 over s squared plus 4 over s squared plus 1 and break this in partial fractions. Because only s squared appears here, I can use substitution called s squared u. So this will be 1 over u plus 4, u plus 1. Now I shall work with u like in the previous example, and then go back to s squared. So we are looking for 2 simple partial fractions like this. And writing common denominator, this will be a u plus 1 plus b u plus 4 over u plus 4 u plus 1. Comparing tops, 1 equals a u plus 1 plus b u plus 4. When you take u to be negative 1, you get from here 1 equals 3b. So b is 1/3. And when you get u to be -4, the question becomes 1 equals -3a. So a will be -1/3. And the decomposition is this. 1 over s squared plus 4, returning to s squared plus 1. A is -1/3, and here we write 1 over, not u plus 4, but s squared plus 4, returning to s squared, and plus 1/3, 1 over s squared plus 1. Now, if we multiply throughout by s, we shall come to the big X. So the big X now is written -1/3 s over s squared plus 4 plus 1/3 s squared plus 1. And now we can recognize two cosines. In the first case, k will be 2. In the second case, k will be 1. So this is -1/3 Laplace cosine 2t plus 1/3 Laplace cosine t. And collecting everything inside L, this will be Laplace -1/3 cosine 2t plus 1/3 cosine t. Inside L, we find our solution. Let's write it down. Xt will be -1/3 cosine 2t plus 1/3 cosine t. So that's how we solve this equation using Laplace transform. I shall do one more. Number 8. Section 10.2. Number 8, x second plus 9x equals 1 this time on the right side. And initial conditions are zeros again. Okay, in number 8, in number 6 we had on the right side cosine. This is actually simpler. Again, we apply Laplace transform to both sides. 9 times Laplace x equals Laplace the function 1. Using forms for derivatives. Now, because the initial conditions are zeros, we can skip x0, x prime 0, and just write on the left side big S with big X plus 9 times big X, and Laplace of 1 is 1 over S. So we factor the big X, s squared plus 9 equals 1 over S. Solving for the big X, this will be 1 over S squared plus 9 here. And then we had to break this in partial fractions and to invert. Looking for simple partial fraction with s, and for the quadratic expression we had to write bs plus c over s squared plus 9. Okay. Writing common denominator, on the right side this will be a s squared plus 9 plus bs plus c times s over s squared plus 9. Comparing tops, we come to this equation. 1 equals a s squared plus 9 plus bs plus c s. We have three coefficients, a, b, and c. One easy number is 0. When you set s equals 0, 1 equals 9a. A is 1/9. What next? Another good technique when we work with the partial fractions, compare coefficients in front of powers of s. So compare coefficients for s squared. On the left side, coefficient for s squared is 0. There is no s squared. On the right side, we have a with s squared, and also there will be bs with s will give you s squared, a plus b. This simple equation. And because we know what is a, from here b will be negative 1/9. What about c? Look carefully at this equation. There is no c on the left side, and on the right side there will be cs, first power. For s, in front of s we have 0 equals c. So c is 0. And now we can write the big X this way. A is 1/9, 1 over s. B is negative 1/9, c is 0, so I'm writing negative 1/9. S over s squared plus 9. We can invert immediately. This will be 1/9 Laplace transform of 1 minus 1/9 Laplace transform. We can recognize cosine 3t here. Cosine 3t. Collecting together, this will be Laplace transform 1/9 minus 1/9 cosine 3t. And inside the brackets is our solution. The solution will be xt is 1/9 minus 1/9 cosine 3t, factoring 1/9, 1 minus cosine 3t. This is our solution. Now, you understand that reviewing partial fractions from calculus is really very important. I'm ending now with the homework. Homework, section 10.2, and this is part 1 of the homework, because we shall continue with this section. Exactly like I did here, at home, you solve with Laplace transform equations 1, 3, 5, 7, and 9. 5 equations for homework. And we continue further next time. Bye for now.